Hi, everyone. Today we are going to go over forces with angles. So, we've been looking at forces on a horizontal plane, but now we're going to look at what if that horizontal plane is shifted? What if we put that plane at an angle? Or what if we apply a force at an angle? So, there are a couple of things that are worth noting before we even get started today. The very first thing is that normal force is not automatically the same magnitude as weight. Okay, because if I apply a different force in a direction, kind of in the y direction or in the direction that the normal force is, either against that normal force or with that normal force, then I'm going to change the normal force. Okay. So what I mean by that is if you take a look at our very first diagram here in the top left hand side, you are going to see that we have a force of gravity going down and then we have a normal force going up. Now, in this case, we have two forces that are equal and opposite to each other. Okay. The sum of forces is equal to zero because the object is not accelerating. And so, therefore, the sum of forces is also equal to the normal force minus the mass times gravity. Then we see that the normal force is equal to mass times gravity. But if you look at this diagram on the right, diagram B, you see that a person is pushing that box down now. So now you not only have your mass times gravity down, but you also have your 40 Newton force down. And so the sum of your forces, still zero because it's not accelerating, the sum of your forces are your normal force up minus your mass times gravity minus 40. So if you rearrange that, you end up getting that the normal force in this case is equal to mass times gravity plus 40 newtons. And it's almost because that person is working against the surface by an additional 40 newtons. Now, if you go directly down here, you have a person pulling that box up with a force of 40 newtons. Now, they're not pulling the box up to start to move it, it hasn't moved yet. What they're doing is they're pulling up with a 40 Newton force, and so they're pulling along with the normal force. So it's almost like they're helping the surface in this case. So our sum of forces is equal to zero because it's not accelerating. And that's equal to our two upward forces, which is normal force plus our 40 Newton, and then minus mass times gravity. So what we end up getting is that our normal force is equal to mass times gravity minus our 40 Newton force. Okay. Now, another situation where your normal force is not equal to your weight or your mass times gravity directly down is when you have a force on an incline. When you have a force on an incline, say you have a box here. And then when you have that box, you have your mass times gravity goes straight down. And then you have your normal force is at a perpendicular motion or perpendicular direction to your incline. So what ends up happening is the normal force is counterbalanced with only one force here. And this is your weight in your y direction. So the normal force in this case is equal to your weight in the y. And we're going to look at that in the next slide. So when you look at this question, a block is being pulled up a ramp that has friction. So let's draw our free body diagram. We have our mass and we have our force of gravity in this direction or our weight. We have our normal force perpendicular to the surface. We have our force of our pull or our applied force. And then we end up having our frictional force. And our frictional force can be written as just a lowercase f or an f sub f. Okay. Now, if I want to break this into different categories, the first thing that I want you to see is my force of gravity is actually my hypotenuse, okay, of a triangle. And that triangle is my force of gravity in my y, okay? And then that triangle is also my force of gravity in my x, okay? And this angle right here is the same, that theta right there is the same as this theta right there. Okay, so what we see is we see that the force of gravity in the x direction is equal to force, because this is a 90-degree angle, force times sine theta. And our force of gravity, and its force of gravity, our force of gravity in our y direction is equal to the force of gravity cosine theta, because it's adjacent. Okay, so if you're going to end up breaking up so the next thing that you're going to do is you're going to break up your forces in your x and y. When we're looking at a simple coordinate system, we have our plus y plus x minus x. And if what I want to do is I want to turn that on the edge a little bit, and I want to make this my plus x plus or minus x, and then at a 90-degree, I have my plus y and my minus y. And then I want to break my forces into my force in my x direction and my force in my y direction. Okay. And when I look at those forces, let's say, for example, let's say that our force or our box is not accelerating. So it can be sliding at constant velocity, okay? Or it could be not moving. So the sum of my forces in my x is equal to 0, and the sum of my forces in my y equals 0. So what are my forces in my x? Well, my x, remember, is here and here. So my forces in that direction, my sum of forces are my force applied minus my force of gravity in my x minus my friction. So I end up getting 0 is equal to my force applied minus my force of gravity times sine theta minus friction. Or my force applied is equal to force of gravity sine theta plus friction. Okay. Now you might be thinking, why are you even solving this? Well, I'm solving this because it's very important to be able to solve these questions with just the variables. Because if you can solve the questions with just the variables, then you can solve them with any set of numbers. Okay. So now we're going to look at our F in our Y direction. Well, our sum of forces in our Y direction is 0. Our sum of forces in our Y direction is also equal to our normal force going up and minus our force of gravity in the y direction. And let's double check. We have this force going down, this force going up. It doesn't look like we have any other forces in our y. So we end up getting 0 equals normal force minus force of gravity in our y. So our normal force is equivalent to our force of gravity times our cosine theta. Okay. So let's look at another situation, another scenario that would be very common. In this case, you have a tightrope walker, and you have a rope that has formed an angle, two angles maybe. Maybe they're the same, maybe they're different. We're going to call that angle 1, and we're going to call that angle 2. Okay, so let's draw our free body diagram. Our free body diagram is going to be our force of gravity going down, and then we're going to have what I'm going to call tension 1 and tension 2. Now, tension 1 and tension 2 can be broken down into their components. Okay, so in this case, we have our y, our tension 1 in our y. Okay, and what's that equal to? Well, that's equal to tension 1 sine theta 1. Okay, then we have our tension 2 in our y, which is equal to tension 2 sine theta 2. Okay, and then we end up having our x values, tension 1x, tension 2x. Okay. Now, if I'm looking at tension 1x, I'm looking at tension cosine theta 1, and tension 2x is tension 2 cosine theta 2. Okay. So when I look at those, I can figure out what all of my values are. I can figure out what my tension is. And again, I have not given you any questions. This is not about the numbers. This is specifically about how do you solve these problems. Okay. Because if you can solve it this way with the variables, you can solve any problem. So let's look at our sum of our forces in our x direction. Well, the sum of our forces in our x direction is 0 because the object is not accelerating. And the sum of our forces in our x direction are T1x minus T2x. So because those are equal to 0, I know T1x is equal to T2x, or T1 cosine theta 1 is equal to T2 cosine theta 2. Okay? And then we're going to look at our y values. Our sum of our forces in our y direction is equal to 0 again. So our sum of our forces in our y direction is equal to, well, let's look at what we have. We have tension 1y plus tension 2y. And those are balanced out, so minus my force of gravity, which is mass times gravity. So I end up getting 0 is equal to tension 1 sine theta 1 plus tension 2 sine theta 2 minus mass times gravity. So I could figure out what mass times gravity is. My mass times gravity, or my weight, is equal to tension 1 sine theta 1 plus tension 2 sine theta 2. Again, it's not about the numbers. It is about understanding how to solve these problems. But we're going to go ahead and take a look at some sample problems. So in this case, I have a 350 kilogram block of ice, and it's being pushed across a frozen pond so that friction is negligible. Okay, so when you have ice, you're going to consider friction being negligible. And it's being pushed by a force, a 2000 Newton force, that's applied at a 12-degree from the horizontal. So this is going to be 12 degrees, and this is a 2000 Newton force. Okay, so in this case, you also have force of gravity going down, and then you have your normal force going back up. And the question is, what is the acceleration of the block of ice? Okay, well, it's the block of ice is going to accelerate in one direction. If you look at the forces, you can tell that the box is going to end up accelerating this direction. Okay, so we know that the sum of our forces in our x direction is equal to mass times acceleration. We know that that's also equal to 2000, your force of x, we'll say force applied in your x direction. Okay, so we end up having mass times acceleration is equal to 2000, and we're just dealing with this force right here. So 2000 cosine 12, or my acceleration is equal to 2000 cosine 12. All of that is going to be divided by our 350 kilograms. So that's going to end up giving us a value of 5.6 meters per second squared. The next question says, how much upward force does the surface of the pond need to exert? So how much upward force? We're basically being asked, what is the normal force? Okay. And we're looking at basically the sum of forces in the y direction. And we know the sum of forces in the y direction is equal to 0 because it's not accelerating in the y direction. We also know that the sum of forces in the y direction are equal to, We have our force of gravity going down. So let's look at our upward force first. We have our normal force minus our force of gravity, which is mass times gravity, minus our 2000 sine 12. Okay, because we're just dealing with this force. We're dealing with our force applied in our y direction. Our force applied in our y direction is equal to our force applied, and then that's going to be sine theta in this case because it's the opposite side. So we end up getting that that equals 0. So the normal force is equal to mass, which is 350 kilograms, times 9.8 meters per second squared, minus 2000 sine 12. And that is going to end up giving us a value of 3,846. Now, if you rounded that to the correct number of significant figures, because in this question I'm given 2,000 newtons, my correct answer in significant figures would actually be 4,000 newtons. Okay, so now we're going to take a look at a very common problem. If you imagine yourself dangling like a watch or a necklace when you're in the car. When someone accelerates that car, all of a sudden you'll see that watch or whatever it is make an angle. Okay, make an angle. And that's because the motion is going to be the same for the watch or for the necklace. So in this case, we have a boy is playing on a train with a toy yo-yo. And the toy yo-yo makes an angle once the acceleration happens, makes an angle of 34 degrees with the vertical. Okay, so that's what's happening here. Now, if we look at our free body diagram, our free body diagram here is going to be our force of tension, and here is going to be our force due to gravity. Okay, those are the only forces acting in this system. What we're going to do is the question is asking to find the yo-yo's rate of acceleration. That's what we want to figure out. Well, we have our sum of our forces in our x direction, and we have our sum of our forces in our y direction. And this question is just a little bit different because we've been looking at sum of forces being 0, but in this case, our sum of forces in our x direction is mass times acceleration, and in our y direction, it's 0. And the reason in the y direction it's 0 is because our yo-yo is not accelerating in the up and down direction. It's the side to side. So when we look at our sum of our forces in our x direction, we only have one value in our x direction, and that value is our tension in the x direction. Okay, and that tension in the x direction is going to be tension sine 34. Okay, and that's going to be equal to mass times acceleration. So we have mass times acceleration equals tension sine 34. Okay. Now, when we look at our y direction, we have our sum of forces is equal to 0, which is equal to our tension in the y direction minus our force times gravity. Okay. So 0 is equal to tension cosine 34 minus mass times gravity. So we end up having that mass times gravity equals tension cosine 34. Okay, so we have two tensions. I need to solve for one tension. So I'm going to solve for my y. I'm going to solve my tension is equal to mass times gravity divided by cosine 34. And I'm going to take that and I'm going to substitute that in right here. So I end up getting mass times acceleration is equal to mass times gravity over cosine 34 times sine 34. Now we know that the masses are going to cancel, and then we end up having this, the sine over cosine, which is tangent. So our acceleration is equal to gravity times tangent 34. And when we go ahead and plug in gravity there, we end up getting that our acceleration is equal to 6.6 meters per second squared. Okay. Now our next question that we're going to do is going to deal with friction. And so in order to talk about friction or in order to solve problems with friction, we need to understand what friction is. Friction is going to be an opposing force. It's a force of opposition that's going to resist your motion. So the frictional force is a force that resists the motion of two surfaces attempting to slide across each other. Now, something that we know that the force of friction is dependent on number one, how rough the surfaces are, or what we call the coefficient of friction. And we have a coefficient of static friction and we have a coefficient of kinetic friction. Okay. And then also how tightly the surfaces are being squeezed, which means how strong is the normal force. So, our frictional force, this is my favorite equation. This is our physics is fun equation. May you never forget it for the rest of your life. We have our frictional force is equal to the coefficient of friction times the normal force. Physics is fun. Okay. Frictional force is equal to the coefficient of friction times the normal force. Now, we have two different types of friction, and that's what I talked about just briefly ago. We have our static friction, which opposes the attempted motion or the attempted sliding. So static friction is friction that exists when something is stationary. And then kinetic friction, or going back, static friction is the friction that resists allowing or keeps you from being able to move an object. Kinetic friction is your friction in motion. Kinetic friction is the friction that opposes continued sliding for surfaces that are moving past each other. So kinetic friction is friction in motion. So we're going to go ahead and do a few problems on friction. First, we have a certain 350-gram block of wood on a horizontal countertop requires 2.5 Newton force to overcome static friction. So we know that the maximum static friction is going to be opposing this 2.5 Newton force. As soon as we go beyond that, then static friction has been overcome and begin its motion, and a 1.8 Newton force to move it at constant speed. Okay. And that's at constant speed. So that's when we're dealing with kinetic friction. Calculate the coefficient of static friction. So we're really only caring about the static friction. So if we draw our object, our box, we have a force applied. And because our object is not accelerating and it's not moving, we have our frictional force. And our frictional force and our force applied are the same because our sum of forces in our x direction is equal to 0. Our sum of forces in our x direction are equal to force applied minus friction. So our force applied is 2.5 newtons. Frictional force is equal to 2.5 newtons. Okay. We also have our force of gravity going down, and we have our normal force going up. So our sum of forces in our y direction are equal to 0 because it's not accelerating in the y direction. And that sum of forces is equal to our normal force going up minus mass times gravity. So our normal force in this case is equal to mass times gravity. And the question is, what is the coefficient of static friction? Well, we know frictional force is equal to the coefficient of friction times the normal force. So our coefficient of friction is equal to our frictional force divided by our normal force, which is equal to 2.5 newtons divided by 0.350 kilograms because we had to convert grams to kilograms, and then times our 9.8 meters per second squared. And when we go ahead and calculate all of that out, we end up getting that our coefficient of static friction is 0.73. And notice there are no units there because newtons are going to cancel with newtons, which is kilograms times meters per second squared. Moving on to our next question, we have a large steel crate of 900 kilograms is being pushed horizontally across the steel floor by an 8,000 Newton force directed along the horizontal. Find the acceleration of the crate and the distance it will travel in 3 seconds. So here we have our object and we have an 8,000 Newton force. Okay. And it is being opposed by friction. Okay. And you have your normal force and you have your force of gravity. Now, something that you do need to know for steel is you need to know that the coefficient of friction, your coefficient of friction in this case, or your coefficient of kinetic friction, is going to be equal to zero point 0.6. And that's a value that you can get from your textbook. Okay, but it's typically going to be given to you. You do not need to memorize those. And because it's being pushed, we're using the coefficient of kinetic friction. So it goes across the steel floor at 8,000 newtons force directed along the horizontal. Find the acceleration. So we know that our sum of forces is equal to our mass times acceleration. We know that the sum of forces in the x direction are also equal to 8,000 newtons minus frictional force. So mass times acceleration equals 8,000 newtons minus our frictional force. So we need to figure out what our frictional force is. Well, our frictional force is our coefficient of friction times our normal force, which in this case, because it's on a horizontal plane, is equal to mass times gravity. So we end up getting that that's equal to 0 0.6 times 8,820, which is your mass times gravity. That ends up giving us a value of 5,292 newtons. I'm going to go ahead and plug that in, 5,292 newtons. And so I end up getting 900 times acceleration is equal to 8,000 minus 5,292. So I end up getting that my acceleration is equal to 3.01 meters per second squared. Then the next question is, how far does it go? Well, we know it starts from rest. So we know we can use this equation, v initial xt plus 1/2 at squared, because that's going to end up canceling. So you end up having 1/2 times 3.01 meters per second squared times our 3 seconds. So 3 squared, which ends up being equal to 13.5 meters. Okay. And then our very last question for today, we have a suitcase with a mass of 35 kilograms is being pushed at a constant velocity across a horizontal floor by a 40 Newton force directed at an angle of 15 degrees below the horizontal. So if I have my object here, I have my normal force going up, I have my force of gravity going down, and then I have my applied force, and that is at a 15-degree angle, and then we end up having force of friction. Okay. And it says that it's being pushed at constant velocity. So in this case, we have our sum of forces in our x direction equals 0 because it's a constant velocity. And our sum of forces in our x direction is equivalent to force applied only in the x direction minus the force of friction. Okay. And so we know that our force of friction is equal to our coefficient of friction times our normal force. Okay. And so when we look at that, we know that that's going to be, we have our 0 equals our force applied cosine 15 minus friction. So friction is equal to our force applied, which is going to be 40 newtons, times cosine 15. Okay. And then that's going to end up telling me that it's 38.6 newtons. Okay. That's going to be what our frictional force is. Then the next question is we're looking at what is our coefficient of friction. So we know our physics' fun equation. Because it's moving, we have our kinetic friction. Now, my next question is, what is our normal force? Well, we have to solve for that because we have something helping along in the y direction. Our sum of forces in our y direction is 0. Our sum of forces in our y direction is also equal to our normal force minus our force applied in our y minus our mass times gravity. So we know that the normal force is equal to 40 newtons, okay? 40 newtons sine 15 plus mass, which is 35, times gravity, which is 9.8. Okay? And that ends up giving us a normal force of 353 newtons. Okay? So to find my coefficient of kinetic friction, I do my frictional force divided by my normal force. My frictional force, remember, was 38.6 newtons divided by my normal force, which is 353 newtons. And that's going to end up giving me a value of 0.109, which I'm going to round to two significant figures. So 0.11. Okay. Hopefully that was helpful today. I know that it was long. I know that these lectures have been long, but hopefully they are helping you get through the problems and also helping you understand the concepts a little bit. If you have any questions, please go ahead and reach out.